And like I said, these are very rare. There's a number of reasons for that. The implementation, the fact that you have a lot of possible points of failure when you're bringing these up. The advantage is that the SVC only exists when you have data to send, so you don't have to keep it up all the time. The downside is that there's a lot of circuits set up and tear down. It makes it far more complicated than the permanent virtual circuits, which we'll look at in just a second. And as I mentioned, they're similar to an ISDN on-demand circuit. These would be great for backups. They never really got that popular. Again, I wouldn't commit too much time to learning about the details behind these, other than just to know how they are different from permanent virtual circuits. And that brings us to permanent virtual circuits, or PVCs. And most of the time when you're talking about a frame relay circuit, you'll refer to it as a PVC. VC, or virtual circuit, is more generic, since PVCs are pretty much what everybody uses. It's generally referred to as a PVC. Anyways, you can guess from the name, permanent virtual circuits are permanent. So unlike the SVC, you don't have to bring them up and tear them down. They're always on, basically. So anytime that you need to send data, you can go ahead and send it over the PVC. Of course, the downside to that is that when you're not sending data, that PVC is still up, but it's not that big of a downside. So the SVC versus PVC is kind of analogous to an always-on cable modem versus the old school dial-up modem, where you had to establish a connection to a modem bank before you could get on the internet. So if you remember the 4 operational states from an SVC, a PVC only really has 2 operational states, and that's transferring data or not transferring data. The difference with the idle is that it's not going to be terminated when the idle period ends. So you could be idle for days if you want, not send a single bit across the frame relay cloud, or you can transfer data all the damn time. As stated earlier, the overwhelming majority of frame relay virtual circuits will be PVCs. Data Link Control Identifier, DLCI, which is pronounced DELCI. That's how you're going to hear it 99% of the time, is DELCI. This is going to be a 10-bit value. It's stored in a field. Actually, it's 2 fields. We'll see that when we take a look at the frame relay header in just a bit here. But it's a 10-bit value that is used as the frame relay address. So you can see 2 to the 10th power leaves you with 1024 possible DELCI values. Of those DELCI values, only 16 through 991 are currently available for use. DELCI 0 and 1023 are reserved for LMI, which we'll look at in just a bit, and then there's a few of them that are reserved for other purposes. So DELCIs are layer 2 addresses, and for those of you that are familiar with Ethernet, they are analogous to the MAC address in the LAN world. Unlike Ethernet, though, frame relay doesn't have a dynamic mapping protocol. There is something called frame relay inverse ARP, and we'll look at that. Works similar to address resolution protocol in Ethernet, but not exactly. So there's 2 big differences. One, there's not really an ARP or frame relay, and the other thing is that unlike the MAC address, well, technically you could have an exact same MAC address. It's very rare that that would happen, but for most purposes, MAC addresses are unique for each device. In frame relay, DELCIs are not unique for each router slash DTE slash device. You can have the same DELCI for your office in Bangkok as you do for your office in Minneapolis. They are locally significant only. Now, there are extensions to LMI that can make them globally significant. We'll look at that in other lessons, but generally they're locally significant only. And we'll take a look at that local significance and how that factors into frame relay design and implementation in much more detail in further lessons. But just keep in mind, those are the 2 important differences, is the lack of a true address resolution protocol and the lack of globally unique layer 2 addresses. And what this means for you is that when you don't have an address resolution protocol, you're going to have to manually map the layer 2 to layer 3 addressing, and we'll see that in quite a bit of detail coming up. So looking back at our triad of routers for our frame relay connection, you can see here how the DELCIs come into effect. So in this case, on router 2, you've got DELCI 201, and that connects you to the cloud. And then you have 301 here. On R1, you have 2 DELCIs, and this will get into a lot more detail later, but you can have multiple DELCIs connected to a single serial interface. Yeah, it'll get a little bit complicated, but we'll go into more detail about that later. Just know for now that you can have multiple DELCIs assigned to the same physical interface. So basically what R2 is going to do is it's going to say, I need to send a packet to R1. So it's going to say I've got R1's IP address, and that is 10.1.123.1. I need to know which virtual circuit to send that over. And so you'll have to have this mapped address. The IP address of R1 will have to be mapped to the layer 2 frame relay address, or the DELSI. This slide shows how the locally significant aspect of the DELSI comes into play. So in the previous slide we just had the 3 routers, and now we have a 4th router. So again, we have 2 DELSIs that are assigned to this serial interface on R2. We have a connection going back to R1, which is going to use DELSI 201, and then one that's going to the new router, router 4, which we're going to use DELSI 301 for. But if you're looking at this, you're going to say, oh wait, there's already a DELSI 301 and that's assigned to R3. That's perfectly fine. There's no connection existing between R2 and R3 at this point. What you have to think of when you're looking at DELSIs is that a DELSI is really going to be a combination of an IP address and a virtual circuit. So in this case, there's not going to be confused. There's not going to be traffic confusion when R2 says, I need to send traffic to R4. R4's IP address is, let's say, 10.1.123.4. Go ahead and map that to DELSI 301. So when I'm sending data to R4 over the frame relay cloud, the router is going to say, okay, well, I know where the IP address is. It's mapped to 301. Let me send information out DELSI 301. It's going to send this out. It's going to hit this frame relay switch, and it's going to get switched over through the frame relay cloud to come out this way. Does not matter that this exists already as 301 because this traffic is not going to be confused. So that's the significance of the local significance, in that it doesn't matter that this has already been used someplace else. It doesn't come into effect as long as the mapping between the layer 3 protocol address and the layer 2 DELSI is unique. Quick look at the frame relay header. Not going to go to a whole lot of detail. Right up here, this is actually a frame relay frame, not a packet. Again, I'm not going to get mired in semantics. So you can see here that there is a portion here that's called the header, and it's nice to look at this. This is the encapsulation. So it starts with the flag, and basically the flags just to say, here's the beginning of the frame relay frame. And then this flag says, okay, we're done with this frame relay frame. Pretty simple frame structure. You have a header. We'll take a look at that in just a second. You have the payload, which is going to be your layer 3 and above information, and again, that is variable length. It's not fixed length. And then here's our FCS. This is our frame check sequence. This is our real basic error checking mechanism within the frame. So then this header, if you break this down, it's got a number of fields here, and we will go into all of these fields in future lessons. A lot of these are important. There's a lot of congestion features in here. Very nice. We'll go through those later. And here's your DELSI, and that's highlighted in orange. You can see here it actually consists of 2 fields. The first field is 6 bits, and the last field is 4 bits. They're always used all 10 bits, so it's that 10-bit value. And now we're on to LMI. And LMI is Local Management Interface. Like I said, you'll always hear it referred to as LMI. And it's a signaling standard used between routers and frame relay switches. It's going to have information about keep alives, global addressing if you decide to use that, and then IP multicast and some other extensions to the frame relay protocol. In the most basic cases, it's going to be keep alives between your router and the frame relay switch, as well as information about which virtual circuits are available on that connection. The other stuff like IP multicast and global addressing, those are pretty much optional extensions that may or may not be offered by your carrier. Anywho, there's 3 forms of LMI. There's Cisco, ANSI, and then Q933A. ANSI is generally referred to as Annex D, and Q933A is generally referred to as Annex A. And although this LMI type is Cisco, it's not proprietary to Cisco devices. It's the Gang of 4 standard that we talked about a little bit earlier that was developed in 1990. The big difference between these is that they use different DELSIs to communicate. So remember we had some reserved DELSIs, and 2 of those were DELSI 0 and DELSI 1023. They were used for LMI. So you can see here that Annex D and Annex A both use DELSI 0, and then the Cisco LMI uses DELSI 1023, and you'll see that on a packet capture that the Cisco uses 1023. Annex D and Annex A both use DELSI 0. Now the important thing with LMI is that you have to be using the same LMI that your frame relay switch is using. So if you're on a router and you're connected to the frame relay cloud, you have to match your LMI with whatever the frame relay switch is running, whether it's Cisco, Annex A, or Annex D. Luckily for us, Cisco has a mechanism called LMI AutoSense, and it's automatically going to determine which LMI type is being used. When this first got rolled out, it had some problems, so you might see situations where you do have it hard-coded, and you definitely can hard-code it. You can specify the LMI type and hard-code it. But nowadays, LMI AutoSense works so well that generally you don't need to go in and hard-code it unless you're going through a troubleshooting process.